Recently, we've been integrating functions of two variables over regions in the plane. And now what we want to do is integrate a function of three variables over a region in three-dimensional space. So let's talk about what that means. The region that we integrate over doesn't have to be a rectangular box, although in this picture we're looking at, it is a rectangular box. It doesn't have to be. It could be a more general region. And how do we integrate a function f of three variables over a region in three-dimensional space? Well, what we do is we take our three-dimensional region, we chop it up into tiny pieces, we compute the contribution of each piece, and then we add up all those individual contributions. It's the same pattern that integration always follows. Now, so we chop up the region we're integrating over into tiny pieces, and we compute the contribution of each piece, and then we add up all those individual contributions. Now let's look more closely at how do we compute the contribution of each tiny little piece. Let's say that the total number of pieces is n, where n is some very large integer. And let's say that each of the pieces are labeled D1, D2, D3, and so on, all the way up to D sub n. And let's say we want to compute the contribution of the ith piece. The way we do that is we select a point xi star, comma yi star, comma zi star. This is a point that belongs to the ith piece. And this point is selected arbitrarily. And now we're going to evaluate our function f that we're integrating. We're going to evaluate f at this point. And then we're going to multiply by the volume of the ith tiny piece. And this number, this is the contribution of the ith piece. So next what we do is we just add up all these individual contributions. So we just sum from I equals 1 to n of f of xi star, yi star, zi star, delta vi. We add up all these individual contributions, and this sum is what we call the integral over d of f dv. This is the notation we use, the integral over our three-dimensional region D of the function f dv. This notation dv indicates that we're doing a volume integral. Now here, we only have approximate equality. What this sum here is called a Riemann sum. This Riemann sum gives us a good approximation to this integral. And if we chop up our region D into very, very tiny pieces, then this approximation is very good. It's a very good approximation. But if you want to make the approximation even better, then just repeat the process. Chop up D into even tinier pieces next time, super tiny. And then we'll get an even better approximation here. So this integral that we're defining right now is actually a limit of Riemann sums. It's a limit of sums like this as the size of the individual pieces is getting smaller and smaller and approaching zero. This integral is a limit of Riemann sums like this. Now let's give this a physical interpretation. Here's a physical interpretation that I often like to think about when I'm understanding conceptually the meaning of integrating over a region in three-dimensional space. The region D that we're integrating over, you could think of it as being a physical object. And this function f tells you the density at each point inside the object. And here, when we're computing the contribution of the ith tiny piece of our physical object, let's think about what this means. This term, that's the density at a point inside this ith tiny piece. We're taking this density, we're multiplying it by the volume of the ith tiny piece. Density times volume, that gives us the mass of the ith tiny piece. So this is the mass of the ith piece. And now in this sum, we are adding up the masses of all the individual little pieces of our object. And what that gives us is the total mass of our object. Total mass. And that's a nice physical interpretation of integration. When we were integrating over a region in the plane, over a region in the xy plane, so when we were doing double integrals, it was possible in that case to visualize the graph of the function that we were integrating. That graph is a surface, and then it was possible to give a visual interpretation of our integral as computing the volume of the region under the surface. However, when we're integrating a function of 3 variables, we can no longer visualize the graph of our function f because humans can only visualize 3 dimensions. So we can't have that visual picture anymore, but we can still have this physical understanding. We can still think of f as telling us the density at each point inside a physical object. This physical interpretation is still a very clear conceptual way to think about the meaning of this integral.